Welcome back, reinforcement learning. This session I start the third unit. The third unit first topic is policy function using neural network. Before going policy function neural network, I explain DQN concept. I recollect the DQN concept. DQN is the Q function is implemented by using neural network is a DQN. In DQN is implemented the neural Q function. The Q function estimate the expected cumulative rewards by using Q values. The Q values nothing but action values. Where in DQN it approximate the Q values. It approximate the Q values in order to get the best cumulative rewards. In DQN we are using epsilon greedy approach to explore the best Q values by best Q values. For the exploration we are using additional method, that is the epsilon greedy method we are using to explore the rewards of the actions, and we also using the replay buffers to store the experiences means the states, actions and their rewards and next states. These experiences we are stored in replay buffer to stimulate the learning process. We are required the experience buffer in DQN concept, and we also we are using target network also to stabilize the DQN in order to reducing the oscillations during the training phases. The DQN, the target network, is copy of the Q network. It updated slowly. Okay, in DQN concept we are additionally using the exploitation point of view. We are using additional method like a epsilon greedy method, and we have to store the previous experiences by using we have to store the previous experiences with the experience buffer, experience replay buffer, and to stabilize the learning process by using additional network, that is the target network. In order to these drawbacks, we have to get the best solution, that is the best solution to overcome these additional operations requirement for the in reinforcement learning, that is the policy function using neural network. The policy function neural network, this is the DQN. The DQN, the input is state. The DQN is a Q network. The input is state. The output is action values. The action values are Q values. The action values nothing but a expected rewards of the action for that on the state. Expected rewards of the actions on that state, that is the action values or Q values. The Q network DQN receive the input as a state is the input, and it produce the outputs are action values. Action values are Q values. In previous unit we discussed the grid-based world game. We have the 4 actions. Each action give the corresponding Q values are we have produced in with the DQN. Now we go to the policy function using neural network. The policy function is the strategy, the state actions mapping. Okay, here the state action mapping policy, this is the policy based method, the policy network. This is the policy based method. It has a mapping between states and the corresponding action. This is the policy function implemented with the neural network is called the policy function using neural network. Here we have the different this policy function. Here the policy network or policy function, the policy network nothing but the policy function implementation with the neural network. It receives the state like a state as an input like a DQN, and here output is probabilities of the action, which action we will predicted to which action we will take, that is the prediction of the action on that state, that is the policy network output. Here output is action values. In DQN outputs is action values. Here the output is the probability of the action, which action we will take. Okay, these actions are the prediction of the actions are either probability distribution values or single action values. If there is a single action value, it gives the only one action. If there is the probability distribution values, it gives the distribution of the different actions, their corresponding probabilities of occurring. Here what is the here we are using policy gradient method to optimize the policy function in order to get the maximize the cumulative reward. The policy gradient, we will see the coming chapters. The policy gradient method aims to optimize the best policy function directly by maximizing the expected reward. Okay, these methods use the gradient of the objective function with respect to the network parameters to update the policy. Here the gradient of the objective function we are using to optimize the policy functions. Here we are discussed the two different policy gradient approaches. The first one is stochastic policy gradient, second one is deterministic policy gradient. In stochastic policy gradient, here the input is any policy network nothing but the policy function implemented with the neural network. The policy network we are representing to pi. The input is state, the state is 1, 2, and it produces the outputs is the predictions of the actions. It is the distribution values. If the first action is 0.5, second action 0, 0.25, 0.25. The first action occurring probability is more compared to others. The stochastic policy function accepts the state and returns a probability distribution over actions. It is a stochastic because it returns the probability distribution over actions rather than return a single deterministic action. Okay, it gives the probability distribution of actions, what will they occur with that corresponding action. The indeterminate policy function, it returns only one action. So it returns the only one, remaining all are zeros. In deterministic policy function, take the state as input, it returns the specific action. Okay, it specifies the one action only. Okay, these are the two different policy gradient methods. One is the stochastic, second one is deterministic. In stochastic, it produces the probability distribution of the actions, and deterministic produces the only specific action. Okay, this in exploration and convergence. In DQN, we need the epsilon greedy method or optimized selection methods for exploration and other exploration of the rewards. But here exploration and convergence are inbuilt in policy function. The policy function gives the probabilities of the actions. So based on the probability of action, it not requires any other. So the policy network distribution, it is a uniform initially, then it is in order to optimize the values, it gives the optimize the policy function. So in advantage of the policy network or the value based, the simpler action selection, there is not required any other methods for explorations. No experience replay also not needed in the policy function. Like a DQN requires the replay buffer to store the previous experiences. Their experiences are not required. The policy network directly optimize the policies without requiring the large memory for replay buffers. And natural handling of stochastically. The probability distribution of the actions, the policy network actually handles the exploration during training. Different probability distribution values are there. Which one has the highest? We choose that one in exploration. It is done automatically. That's why the natural handling of the stochasticity. So these are the advantages. We also have some key challenges in policy network. Define the objective function. Okay, in DQN, the objective is the predicted Q value functions and actual functions. We are find the error, that is the mean square error is we are calculating the DQN, that is directly we are calculating the value functions, but the value functions are not, action values are not here. So the objective function defined is the critical in policy function compared to DQN. And exploitation. Exploration we are performed with stochastical probability distribution values, but sometimes it is good or sometimes it is not good, and balancing stochastic and deterministic. So sometimes we are required the deterministic, sometimes we are required the stochastical. So we need the balancing both stochastic and deterministic operations. The conclusion of this session is the policy network is compared to DQN, it not required additional large memories and additional approaches for explanations. The policy network and DQN both are the good methods to solve the reinforcement learning problems. Thank you.